Hey, welcome to the Explainer. All right, today we're diving deep into the hardware, the actual engine that's powering this entire AI revolution. We're going to tell the pretty surprising story of how a piece of tech built for video games kind of accidentally became the absolute brain behind all of modern artificial intelligence.
And, this quote from NVIDIA's CEO Jensen Huang just nails it. The very same technology that used to render these incredible imaginary worlds for us to look at is now literally creating intelligence for us to use. It's a massive shift.
So where does this all start? Well, our story begins not in some high-tech AI lab, but at a pretty standard image recognition contest, just a little over a decade ago. This right here was the moment that basically lit the fuse for everything that came after. That's right, a system running on two just off-the-shelf gaming cards, the kind you could go out and buy, didn't just win this thing, it completely demolished the competition. And that was a huge revelation. It proved that the way a GPU is built, its fundamental architecture, was a perfect, almost accidental match for the kind of math that powers deep learning.
Okay, so why? Why was a gaming card so ridiculously good at this? Well, to get that, we have to look at its core design and just how fundamentally different it is from the traditional processor in your computer, the CPU. And honestly, this analogy is the best way to get it. A CPU is like a specialist. Think of a world-class surgeon. They can perform one incredibly complex operation at a time with absolute precision. A GPU, on the other hand, it's an army. It's thousands of soldiers all doing a much simpler task, like, say, digging a trench, all at the exact same time. Well, it turns out that AI training doesn't need the surgeon. It needs the army.
Now, let's zoom in on that army, because inside that GPU, you've basically got two different kinds of soldiers, and each of them has a very, very specific job. First up, you've got the CUDA cores. You can think of these guys as the general-purpose infantry. There are thousands of them, and they are the workhorses. They're handling all the data prep, the logic, basically getting all the information where it needs to go so the main event can happen. But the real superpower, the game changer, are the tensor cores. These are the elite special forces. They're units of hardware that were designed for one and only one purpose, to just crush the exact kind of matrix math that is the foundation of neural networks. They do one thing, and they do it insanely fast. So to put it another way, think of it like a movie set. The CUDA cores, they're the entire stage crew. They're setting up the lights, moving props, managing the whole production. But when it's time for that big, computationally insane action scene, that's the neural network training, the tensor core stunt team swoops in and executes it with just breathtaking speed. But here's the thing, right? Having this incredible army of processors is totally useless if they're starved of supplies. And in the world of AI, those supplies are data, and it's all stored in the GPU's own dedicated memory, called VRAM. It's such a simple but absolutely vital concept. I mean, what good is a Ferrari engine without any fuel? It's just a lump of metal. The entire AI model, its billions of parameters, all the training data, everything has to fit inside the GPU's super fast memory. If you run out of VRAM, the whole engine just grinds to a halt. And the amount of fuel these things need, it's just staggering. To run a big model, something like Llama 70B, you need around 140 gigabytes of VRAM. I mean, that is way, way beyond what any single consumer GPU has, which is exactly why these huge models need these specialized multi-GPU servers to even run. And it's not just about how big your gas tank is. It's about how fast you can get the fuel to the engine. That's bandwidth. A data center GPU like the upcoming Blackwell has a memory bandwidth that's up to 8 times faster than a high-end consumer card. It's literally the difference between a garden hose and a fire hose. And it is absolutely critical for keeping that powerful AI engine fed. So all of this relentless demand for more memory, for more compute, it brings us to the final piece of this puzzle, the just breakneck race to keep innovating in GPU architecture. What's so fascinating here is that the progress isn't just about making the chips bigger. It's about getting way smarter with the math. Each new generation, from Ampere all the way to Blackwell, has introduced more efficient ways to represent numbers. These things called FP8 and now FP4. It's like learning a type of mathematical shorthand that lets the GPU do way more calculations using way less data. And that just dramatically boosts performance.
So what does all that evolution actually look like in the real world? Well, if you were generating AI art with a top-tier card from 2018, you'd get maybe 20 images a minute. Fast forward just 4 years, and a 2022 card can crank out nearly 4 times as many. That's not a small jump. That is a massive leap in what's actually possible.
And this brings us to the next frontier, arriving with the Blackwell architecture, called FP4. This is a huge breakthrough. It allows the GPU to represent numbers using only 4 bits of data. And the result is, well, it's almost like magic. You can pretty much double your AI speed and fit a model twice as large into the exact same amount of memory. And you do all this with almost no hit to accuracy. It's a huge win.
And this all kind of leads to the big question, doesn't it? As these AI models continue to swell to trillions of parameters, is the path forward just building bigger and bigger, more power-hungry hardware? Or will the real breakthroughs actually come from finding even smarter, more efficient ways to do the math? The answer to that is probably going to define the entire next decade of AI.